So we've continued with the next presentation on the same tone. We are talking about natural gas again. And natural gas engine for commercial vehicles, and Euro 5, maximum power and efficiency. And so our next speaker is Mr. Cruff from EControls. Please, would you?
Okay, well, thanks everybody. I know it's been a long couple days, and I appreciate you sticking with us here. I'm actually really excited to be here today to talk to you about some of the stuff that we've done over the past 20 years, really, in gaseous fuel control, and where some of our technology sits today. So I've got quite a few slides. I'm going to try to buzz through them fairly quickly. Obviously, we'll have a little time for questions at the end, and hopefully I can cover anything then, or we can talk later. So first of all, just a little bit about who we are. You may not be familiar with us at all. We're a major player in the global truck and bus market. You can see the top two markets there. On the left-hand side of the screen, you can see a couple industrial applications. We are in pretty much the #1 provider of gaseous fuel control in forklifts, emissions certified forklifts in the world. As well as in stationary applications as well. On the bottom right, you'll see natural gas production control. These are engines that sit out in the middle of nowhere and run on natural gas wellhead sites, and we're the #1 by far player there. And then you see the recreational marine market. And initially, when you look at that, you might say, what's the common thread between all those markets? They're very different. And really what it is we've gotten into each of those markets when difficult emissions legislation was pending. So that's really how the company got its start, and it's really how we still survive today. So when it comes to Euro 6, we've put a lot of work into it, and that's what I'm going to be talking about today. In terms of where we are in the world, headquartered in Texas and Oklahoma in the U.S., major facility in Hangzhou, China as well, where we do production and development. And we support pretty much everywhere globally. We've got a facility in the Netherlands, a couple other facilities in Asia and in Europe as well, and a plant due to a recent acquisition, which I'll talk about in a little while, out in California. So we're not a prototype house. We've been doing this for a while. We've got a lot of hardware out there in the field, a lot of experience in the field. In heavy duty, medium and heavy commercial, we've got about 300,000 systems in the field overall. In all the markets that I mentioned a couple minutes ago, over 1.5 million systems running out there today. We do have full in-house engine development. We think it's incredibly important for us to help our customers get the application right, not just sell them parts. So we have development centers in the USA and China. We have 15 dynos operational today between those two sites. We are looking to add more in the US as well as in Russia, which is a market that's emerging for us at the moment on propane and natural gas. So our products today meet all the most stringent emission standards in the world, including Euro 6, and I'll talk a little bit more about that as we go. Lots of different customers, pretty much all the big names in our respective markets. I mentioned natural gas production as well as the industrial and heavy duty markets. Specifically to commercial on highway, you can see there major presence in China. Just to give you guys an idea of scale, this year in China alone, just this 12-month 2017 period, China will produce 100,000 natural gas heavy duty trucks and another 15,000 to 20,000 natural gas buses. So it's a massive market, completely different and bigger than anything else in the world. You know, the USA is under 10,000 a year for the combined total of natural gas. So we're a major player there, and we'll put about 45,000 systems into that market this year. We have just announced as well, we'll be on our first U.S. on-road application as well, the Cummins engine, the 12-liter, is going into production right now, and we are meeting the near zero NOx California emissions legislation with that engine as well. So just to give you a little example of who we work on and what kind of applications they are. So what do we do? What do we make and sell? Just so you have an idea, electronic controllers, every form factor you can think of, from 20-some pins to 200. We sell a lot of 90 and 120 pin systems into the Euro 6 market. Really, one of our calling cards is electromechanical components, fuel control devices. You can see there electronic pressure regulators, very high-speed devices, continuous flow valve, which I'll talk about later, wastegate control, lock-off valves, and then a couple of our new products, throttle, electronic throttle, and injectors, which came our way via recent acquisition. Mechanical components, getting the fuel to the electromechanical devices through high-pressure regulators and other types of regulators and boost surge valves and things. And we do provide full systems as needed from the customers, so we will specify or provide catalysts, sensors. We purchase in wiring harnesses. We'll design and purchase for customers as needed. And normally, as their volume grows, they take that over from us. So we did a project, which is the main focus of the talk today, on a 10-liter class engine, targeting Euro 6 emissions levels and targeting very high BMEP and very high efficiency. So when you look at the development of an engine, that's the triangle that's difficult. Efficiency, performance, and emissions, and hitting them all at the same time. That's where the trade-offs really start to come in. So just a little background on why we did this. We wanted to create a viable alternative to diesel engines. Diesel engines, as Dr. Tips has said, have some unique advantages, including low-speed torque, which everybody realizes. And so we wanted to produce something that was viable in terms of replacing that. Meets emissions, highly cost competitive, high BMEP, but not just high BMEP in the high RPM range, high BMEP in the low RPM range, which is really what affects real-world drivability and real-world efficiency. So that was kind of the focus of our project. Before we made hardware, we took a long time actually to go through some different technology options. I'm just going to step through these fairly quickly. This took a lot of time, a lot of effort, a lot of analysis, some test work. But I'm going to go through lean burn plus SCR as what we consider technically viable and economically viable solutions for Euro 6 solution. Stoichiometric combustion with a modified camshaft, Miller cycle camshaft, and then stoichiometric with high EGR dilution. So we're very familiar with lean burn. That's what all our Euro 5 solutions run today. Without SCR, it's a well-established combustion strategy. Many people here may be familiar with it. It's not difficult to control. The issues with this system are the cost of the SCR system, which we've gone over in great detail over the last couple of days. But also, in this case, the cost and durability of the oxidation catalyst. So when you go to Euro 6, a couple people have mentioned you have emissions durability requirements that now come in. And in heavy duty, that is 720,000 kilometers. So that means you still have to be making the regulation nearly 750,000 kilometers down the road. The problem with an oxidation catalyst is it doesn't have great efficiency to start, only about 90%, and it degrades over the life to about 40 or 50% of its original efficiency. So you have to size the catalyst significantly larger than what you'd like to do, and that incurs significant cost. Stoichiometric system, a very simple system here, what most passenger cars run, what a lot of our industrial applications run. Very simple combustion system, well known. The issue here is normally temperature. We're generally dealing with diesel-derived engines here. The issue with a diesel-derived engine is it was designed to run on diesel. The temperatures, especially the exhaust gas temperatures, are limited because of that. That restricts the BMEP level of the stoichiometric engine down to about 14 or 15 bar. So if that's your target, this is a pretty good solution, a very cost-effective solution. If it's not, then and you need to run higher BMEP, then you will start to suffer efficiency losses when you run plain stoichiometric. When you add Miller cycle to it, you can get a couple more bar BMEP, but the boosting system becomes much more complicated because you're either doing early or late intake valve closing. You're wasting some of the pressure in the intake manifold, rebreathing it, or never putting it in the cylinder in the first place, and that limits your BMEP or your torque. And a lot of times to make up for that, you need to run either a dual stage turbo system, a VGT, etc., which is a problem when it comes to cost. So again, in the right application, Miller cycle makes some sense. For above 20 bar BMEP, which was the target for this particular project, and I'll show the results here in a minute, we looked at stoichiometric plus high EGR rate. So here, instead of using excess air as the diluent fluid to cool the combustion process, you're using EGR. In a liquid fuel engine, you can add extra fuel. That cools the combustion process down. You can run richer than stoichiometry. In a heavy-duty application, that doesn't really work for two reasons. One, you run at high load a lot of the time, so you can't afford to overfuel. And two, in a gaseous fuel engine, it doesn't bring you any benefit at all. So it works completely differently. So we have to dilute the charge with something else. Here we chose high EGR. Now there is an EGR cooler that's required. There is an EGR valve that's required. Another control loop in there, obviously. Some more hardware and sensors. However, and which bring out additional cost. However, that cost is offset by the significantly lower cost after treatment device, which is a simple three-way catalyst. So what running stoichiometry with high EGR allows you to do is run a low-cost catalyst and still run high BMEP, which gets you your efficiency and your performance back. So as we go through, as we just look through those again, I'll just talk about that diesel-derived engine one more time. That's normally the primary challenge. And the issue is you would say, well, it'd be great if we did a natural gas engine and we just optimized the engine. But that's not really going to happen. Again, everything comes down to cost. It comes down to economics. And there's not enough volume in most of these applications to do a dedicated natural gas engine. So you end up with a flathead diesel-type combustion chamber, which is limited in temperature capability. And that has to be one of your design considerations when you look at these engines. 10 years from now, 2 or 3 generations down the road of gaseous engine design, maybe we'll have a different solution. But the reality of our world is that most of these are diesel-derived engines. So really, it's a combined system effort to get these engines to work right. The base engine has to be right. The control system has to be right. It doesn't really do you any good to put a bad control system on a good engine or vice versa. You'll come up with a far from optimized solution. So when you talk about the engine, the combustion chamber, which exists in the piston, which is a challenge, is incredibly critical. The camshaft design always wants to be different than a diesel. And the turbocharger match is very different, especially when you're trying to drive high amounts of EGR. And we'll talk about that here in a minute. On the control system side, accurate high levels of EGR are critical. In a diesel engine, you run EGR because you're either trying to control particulates or NOx. Or NOx. You have a trade-off. If you miss a little bit, if you miss extra EGR, you create maybe a little extra soot, and you control your NOx. If you're low on EGR, your NOx will go up a little bit. You deal with it in the after-treatment system. You don't break anything. In a spark-ignited natural gas engine, especially one running high BMEP, if you miss on EGR, you break the engine or you misfire. Those are your two options. So you break it because of knocking, or you misfire and the driver hits his head on the steering wheel. So neither of those are really good, acceptable solutions. So in terms of actual numbers, diesel engines run plus or minus 4 or 5% accuracy for EGR. We're talking here about running plus or minus 1.5% accuracy for EGR. So it's a different technology, it's a different algorithm that's required in sensing technology. Continuous flow fuel injection I'll talk about, and very good charge mixing also critical. I'll also give a brief overview later of our fully integrated algorithm set and how we control the pressure across the engine. That's kind of the last critical piece of the control system. So from a combustion chamber standpoint, I'm not going to go into this in detail. The point is you have to do a lot of work here, and if you get the combustion chamber right, the whole rest of your program is much, much easier. Your exhaust gas temperatures are lower, your efficiency is higher, your spark timing is improved, so everything just gets better. If the combustion chamber is not right, you don't have sufficient levels of charge motion, and it burns too slowly, there's almost nothing you can do to calibrate the engine to get it efficient and high power. You just get into a corner in terms of calibration that you can't get out of. So there's a lot of detail behind that we won't go into today, but it's critical. Camshaft design. We always design with low overlap. That reduces the charge temperature from, we're running cooled EGR. We don't want hot EGR coming back in from the exhaust side through the overlap period of the camshaft. So we reduce the overlap generally compared to the diesel camshaft, which also reduces the propensity to backfire. We do have a manifold full of flammable fuel here, and we need to control backfire completely. We also need to optimize that camshaft for low speed torque and match it to the turbocharger. I talked earlier about the turbocharger. The challenging area there is highlighted in the plot. Driving EGR at low speed, high torque with a fixed geometry turbo is very difficult. We feel a fixed geometry turbo is required for several reasons, durability and cost being the primary ones, but there are other drivers as well, including temperature capability. So this is just an overview of our system. If you've been to our booth, you've already seen that. I'm going to break this down into a couple things, just mention a few features of it. In the intake, this is the air path. So here you can see we do run a humidity sensor that is unique to our system, and which really helps us dial in the correct amount of diluent fluid. You can see also the throttle inlet pressure and the manifold pressure sensor, which helps us control the pressure across the throttle, and the wastegate control valve, which helps us control very accurately the wastegate of the engine. Our fueling system, we do everything after the tank pretty much. So we supply our system with 4 to 6 bar pressure. This is our continuous flow valve, which is a dual stage pressure and volume flow control device. Then we have our cooled EGR path, obviously the EGR cooler in there, and then we've got pressure and temperature sensors for in the gas stream, as well as a delta pressure sensor across an orifice, which is how we do our measurement. I know the Sensata guys talked yesterday. We've done a lot of work with the Sensata guys actually to speed up the response of that delta P sensor, and we've also changed how we run our loop times in our ECM and our algorithm so that we actually capture the pulse flow going back and forth across that orifice and subtract the negative flow, which makes the EGR measurement much more accurate. So that's been a couple year development trying to get that algorithm and that set of hardware correct, but now we're down to that target of plus or minus 1.5% EGR accuracy, which we feel really good about going into production. And then the turbo, just controlling the catalyst. We do run a wideband UAGO sensor in front of the catalyst and a narrow band behind it for OBD requirements. So when we talk about accurate high levels of EGR, just a little more detail. I already talked about the need in a natural gas engine for that versus a diesel, but how you measure the EGR and how you calculate it is also very critical. Again, this is kind of a longer derivation. I'm just giving you the bottom line result here. We believe in direct measurement of EGR, as I just showed with the orifice and DP sensor. If you measure the airflow air mass and deduce or infer the EGR mass, your error is much higher. There are many error contributors here. Your volumetric efficiency calculation is one of them, and you can see the difference between the measuring directly the EGR, measuring directly the air. The air measurement method is much more sensitive to volumetric efficiency calculation errors. It's also much more sensitive to feedback measurement. Every feedback measurement system has error. You have to plan for that. And if you measure the error directly instead of the EGR, It's about 4 times worse. The percentages I'm showing there are percent EGR. So they're huge differences. When you're running 20% EGR, you can't be 4% off, as I mentioned earlier. You really don't want to be 1% off, but you know, we're in the acceptable range with direct measurement EGR. If you just measure air, it's not even close. So that's the bottom line there. Continuous flow fuel injection. So I mentioned the CFV. That is a very high speed, 10 millisecond full range response time type of valve. So we can go full fuel flow to full cutoff in 10 milliseconds with that valve. This is a plot. I'm not sure if you can see it, but the percent difference in emissions in green is an injection-based system, a pulse flow-based system, and in red is the CFV system. And what you'll note is as the load increases, basically load or flow is increasing as you go across the x-axis here, they actually start to come together. And the reason for that is when you run a pulse flow system, the higher the load, the longer the injection period is, and the more it emulates continuous flow. And then when you're at lower loads, the more likely you are to miss your fueling target because you're prone to that injection duration problem. That's not to say that injection doesn't work. There's just a trade-off. So in large engines, we find that continuous flow is much better. Large engines in the 7 to 13 liter class, it's much better to pay for the continuous flow device and the control that brings and reduce your catalyst cost. In smaller engines, the 2 to 5 liter class, it's usually better to go with injection, even though you have a little bit more error on your fueling. The increased cost in the catalyst is less than the differential in the fueling device. So you have to look at the cost as a full system. Whether you're running injection or continuous flow, the key is you have to control the feed gas into the catalyst incredibly closely. So we're showing a plus or minus 2.5% there. You can see that from stoichiometric ratio, lambda 1, phi of 1. You have to control this down in the tenths of a phi, 0.05, 0.02 kind of numbers, to make sure that that catalyst stays at the 98 to 99% efficiency range. So incredibly important. Another thing that gets overlooked a lot with natural gas engines and when you're running EGR in natural gas is that the specific gravity of the fuel and of the EGR is very similar to the air that's coming in. And two gases of similar specific gravity don't really like to naturally mix. So you have to put some effort into getting them to mix. And there's macro mixing and there's micro mixing or diffusion mixing, and both are very important. And so we've devised, we've spent a lot of time. We talked earlier today about some analytical tools, some great presentations there. We've spent about 2 man-years developing the mixing system that you see here to mix both the EGR and the fuel and make sure that we have a fully homogeneous charge entering the manifold so that all the cylinders are even and the fuel and air are fully mixed. So that's great. What happened? Where'd we get? Here's the plot we're most proud of. Here we're showing the red curve, a typical kind of 18-bar natural gas lean burn engine with not fantastic low-speed torque performance. We're showing in the blue typical kind of 23-bar state-of-the-art diesel engine. And we're showing our results from this 10-liter class engine here in green. So just some highlights here. We obviously matched the 23-bar BMEP throughout the range. The high-speed power was greater than diesel. That you might expect with a spark-ignited engine. They work kind of that way. But what you might not expect is that we're in grave danger of breaking the transmission on this vehicle because the low-speed torque actually significantly exceeds the diesel. Our maximum torque is actually at 800 RPM on this engine. So again, that comes down to camshaft, turbocharger matching, and combustion system, as well as getting the right amount of EGR into the engine. From an efficiency standpoint, you come up with a very large high-efficiency operating window. A core of the engine map is right around 200 grams per kilowatt hour. You would say a lean burn engine, hey, I can get 185 grams per kilowatt hour. You can at a certain point, but you cannot get the broad map engine efficiency that you can get with the stoichiometric EGR-based system. 2/3 of the map under 220 grams. If you look at World Harmonized Transient, or any transient cycle actually, this engine map will always outperform the lean engine, even running optimized lean efficiency. We did have some wastegate issues on this particular project because it was a research project, and in production we would have upsized the wastegate essentially and fixed that high-speed issue. Exhaust gas temperature pre-turbine here, everything under 740 degrees across the whole map. COV of IMEP, or the stability of the combustion, incredibly good. I've worked on almost no SI engines that are actually this good. Again, up there at that peak power point, we were hurt by the wastegate issue. Of course, that would go away in production, so it's not really something we worried about. But again, that combustion stability comes because of the speed of combustion in the chamber due to the mixture that we dialed in. On emissions, WHTC was mentioned earlier. That's what we ran this on, hot and cold weighted results. After deterioration factors are applied, we were below 50% of the limit, so well within the limit. Again, like I said, we have no issues hitting Euro 6, near zero NOx in the US, or actually Euro 7 we hit in a couple of regions with this same hardware. We talked earlier about the fully integrated algorithms, boost, EGR, and throttle. Just want to give you a quick example. This is a different engine. This is a 12-liter engine. Here we did not change the base engine hardware, so this is fully down to the control system. What you can see there is the two different cylinder pressure curves, the baseline in the blue and ours in the green. The bottom line here is we're producing the same torque with slightly lower manifold pressure, less pumping, less delta P across the engine by managing the wastegate, the throttle, and the EGR valve continuously. And that nearly 4% reduction in airflow and a stoichiometric engine translates into roughly 4% reduction in fuel flow, and at equivalent torque, of course, that's the same BSFC, or that's a 4% improvement in BSFC. So there's a lot of numbers there, but that's the bottom line. So far we focused, and I've shown you some stuff in the kind of 6 to 13 liter class. As a result of our recent acquisition of IMCO Industrial, we've now designed a cost-competitive and more packageable offering for the 2 to 5 liter class, which we think is very applicable to the Indian market. It comes with all the same technology that I just talked about, all the mixing, all the control algorithms, etc., but is easier to package and even more cost-effective. So injection-based fueling here. Show you a couple pictures. So going back to this, that was our continuous flow map. Here it is with injection. Completely eliminate that large CFV, which is difficult to package on smaller engines. Put the injectors right on the EGR and fuel mixing assembly. Downsize the mixing assembly for this flow range, and this is the result. Just a couple dimensions here to show you. It's about 200 millimeters long, 90 millimeters wide, very, very packageable system. And just as a direct back-to-back comparison, if you brought in the fuel from a remote device like a CFV, this is what the mixing device would look like. And here's what it looks like with the package injectors and fuel temperature and pressure sensor. So we're pretty happy about that. If you don't want to run EGR, again, going back to those 14, 15 bar engines, we can make it even simpler and smaller, and we're working on that as well. So in summary, we did reach 24 bar BMEP at 740 degree max EGT limit with excellent misfire and knock margins. We could do better with a better turbo match. We ran out of time on this project. If we limit it to 720C, which is sometimes a limit that turbo manufacturers have on certain materials, 1,200 pound-feet there means 21 bar BMEP, still 380 horsepower out of a 9.7 liter engine. So in conclusion, with the optimized base engine and the control system working together, we found fantastic results, and are now working on applying this. We've got about 20 Euro 6 projects in the works right now, with production starting in around 2019 and going from there. So, sorry I did run over a little on time there, and said a lot of words, but hopefully you caught most of it, and if there's any questions, I guess we can do that now.
Thank you for the presentation. And before we close the session, and before seeing Ben address us as closing the summit, still a few minutes for any question that you might have or any doubt. So I guess I impress all of them.
Either that or put them to sleep.
Okay,
it's hard to tell. Yeah.
Thank you very much for the presentation.
Okay, thanks.
Okay, thank you very much for the chair stepping in at short notice, and also for the presentations. It was good to see, some quality research and results, and also the presenter earlier who's now left. It was a good overview, I think, of the options that are available. So I hope that you've enjoyed today. If you have any thoughts, make sure that you fill out the feedback form that we've put in front of you. All your feedback is very welcome, and it's good to hear as we go ahead for next year, and we want to make sure the conference is really suited towards you. I'd just like to extend the thanks to everybody who attended. I hope you had a good time. The conference is now over, so you can all return home. I hope we've all enjoyed the discussions and the presentations, and so I just want to say thanks again to the chair and everybody who presented. Thank you very much.